The Mach 9, 6 X-43A hypersonic scramjet has a message for the U.S. military. Key points and summary: NASA's X-43A proved an audacious idea: use a scramjet, a jet that breathes air at supersonic speeds, to fly near Mach 10. Dropped from AB-52 and boosted by a Pegasus rocket to test speed and altitude, the 12-foot research vehicle ignited its hydrogen-fueled scramjet for seconds that made history: Mach 6, 8 in March 2004 and Mach 9, 6 that November. The three-flight HyperX program ended after meeting its core goals, as funding and priorities shifted. Though short-lived, X-43's flight data, materials lessons, and control strategies became the starting point for later U.S. hypersonic efforts and the benchmark for air-breathing speed. X-43A, NASA's Mach 9, 6 hypersonic proof of concept. By the late 1990s, engineers had squeezed about all they could from wind tunnels and simulations of scramjets, supersonic combustion ramjets. The catch: scramjets only make sense at hypersonic speed, where air rushing through the inlet stays supersonic as it mixes with fuel and burns. To know if scramjets truly work, someone had to fly one, close the loop on inlets, ignition, combustion stability, and controls in the real, high-temperature, high-pressure environment where models get shaky. That was the point of HyperX, a modest, high-risk program built to turn decades of lab work into seconds of flight data that textbooks couldn't provide. The concept: small vehicle, big questions. NASA kept the airframe tiny, about 12 feet long, to simplify logistics and focus on the engine. The X-43A would not take off on its own. Instead, AB-52 would airdrop a modified Pegasus rocket booster with the X-43A riding on its nose. The booster would sprint the stack to the target speed and altitude, then the research vehicle would separate, open its inlet, and run its hydrogen-fueled scramjet for a short, carefully planned burn. After that, it would glide unpowered into the Pacific. Every second mattered. The goal wasn't endurance, it was to prove air-breathing propulsion beyond the lab. The path to success wasn't straight. The first flight attempt, 2001, ended in failure when the booster went out of control and the range terminated the mission. That painful lesson forced 2 years of fixes, better modeling, cleaner controls, and a tighter booster/vehicle integration plan. When HyperX returned to the air in 2004, the approach was the same, but the engineering was wiser. What followed were 2 record flights that validated the entire idea of air-breathing hypersonics. How X-43A reached Mach 6, 8, and then Mach 9, 6. Think of the profile as a relay. Carrier phase: AB-52B hauls the stack to altitude off California's coast. Boost phase: the Pegasus first stage lights, pushing the stack up to the test window, tens of miles high and already at hypersonic speed. Separation: the X-43A breaks free, stabilizes, and opens its inlet, the moment of truth. Scramjet burn: with hydrogen flowing, supersonic air rushes through the engine, combusts, and produces forward thrust. There are no compressors or turbines, just geometry, pressure, fuel, flame, and timing. Data harvest: sensors soak up temperatures, pressures, thrust, and control behavior before the vehicle glides to a planned splashdown. On March 27, 2004, the engine lit cleanly and sustained a burn around 11 seconds near Mach 6, 8. On November 16, 2004, the third vehicle repeated the feat in a hotter regime, peaking near Mach 9, 6, the fastest air-breathing flight on record. The burn lasted mere seconds, but at those speed, seconds are a lifetime of data. What those few seconds proved: combustion stability: supersonic flow can carry flame downstream before it releases useful energy. X-43A showed that you can ignite and sustain high Mach combustion in flight. Integrated aeropropulsion: airframe, inlet, and nozzle must behave as one system. X-43's results validated airframe integrated scramjet design assumptions that tunnels could only approximate. Controls at the edge: even brief burns demanded exquisite attitude controls so the engine saw the right airflow, the vehicle's guidance and control laws delivered. Materials and heat: temperatures soared. The team learned where coatings, thermal protection, and structures meet their limits, and how to design around them. Why the X-43A program ended: HyperX was always scoped as a 3-flight effort, one attempt at Mach 7, which failed and drove redesign, then Mach 7 and Mach 10 targets once the stack worked. After the 2004 successes, NASA had the data it asked for. Meanwhile, national priorities and budgets shifted. Post-2004, Funding emphasized other aerospace goals, and the Air Force took the lead on follow-on air-breathing hypersonics, eventually fielding the X-51A demonstrator years later. In short, X-43A wasn't canceled midstream so much as concluded after meeting its narrow objectives, with resources redirected to the next phase under different sponsors. Why Mach 9? 6 still matters. Breaking Mach 9.6 with an air-breathing engine wasn't just a speed stunt. It confirmed that scramjets can operate where rockets once had the field to themselves. That matters for any future system that wants high-speed, high-altitude flight without carrying oxidizer, rapid response strike, long-range ISR, or even stages of access to space concepts. The X-43A also set a benchmark. It's one thing to model hypersonics, it's another to fly it and bring home the data. Limits, myths, and what X-43A wasn't. The X-43A was not a prototype airliner or a practical weapon. It didn't take off by itself, didn't land, and didn't cruise 4 minutes at Mach 9+. It was a surgical experiment, prove the engine physics, validate the integration, and retire risk. Turning that into an operational vehicle requires endurance, thermal management, reusable structures, large envelope controls, and sustainable fuel systems, the hard, unglamorous work that follows any X-plane triumph. The legacy in today's hypersonics. Look at modern U.S. hypersonic efforts and you'll find X-43 as fingerprints everywhere. Engine/vehicle co-design. HyperX hardened the habit of designing inlet, isolator, combustor, and nozzle with the airframe from day one. Flight-first mindset. Programs now aim early at flight-relevant conditions, not just tunnels, to spot the surprises that only real air uncovers. Data as a force multiplier. The X-43A data set still anchors validation of codes and digital twins used to design next-generation vehicles. Final take on X-43A. The X-43A was a tiny machine with an oversized impact. In 3 flights, 2 that counted, it moved scramjets from theory to flight-proven reality, set an air-breathing speed record, and handed the baton to follow-on programs with a map of what works and what breaks. That's exactly what the best X-planes do. Answer the decisive question, then get out of the way so the next generation can build on the answer.